Hi, I'm Michael Wolf, PGI Compiler Engineer. Here I'm going to be talking about the future of data management with OpenACC when unified memory comes online. Now we can think of the device memory as relative to the host memory, more or less like we think about cache memories and SCRATCHPAD memories. Let me draw a picture of today's system, a CPU with a cache memory. So up here, we've got our multi-core CPU. Down here, we have our very large system memory. Now we all know that on the CPU there's a level 1 data cache and a level 1 instruction cache, and there is typically also a level 2 cache and a very large last level. On most Intel systems would be a last level 3 cache. Very large cache memory. Data that you load or store from the device, from your core, will get loaded into these cache memories automatically by the hardware. You don't have to do anything. In fact, you don't want to do anything. You don't even have to think about the cache memories. You don't have to think about how big they are. You don't have to think about whether there's conflicts between two different loads. Are they going to conflict in the same cache? Because all that's managed in the hardware. So cache memories are managed entirely by hardware, but it's not the only option that one has available. On many systems, particularly embedded systems, they have a core and they'll have a little SCRATCHPAD memory. SCRATCHPAD memory is managed entirely by software. So it's a different address space, uses different load instructions. With an embedded system, I can load data from my system memory and then store it in my SCRATCHPAD memory. Now the advantage of a SCRATCHPAD memory relative to a cache is in software, if I store something in the SCRATCHPAD memory, it stays there. I know it's there. I can depend on it being there. I know the load will be absolutely a fast load from the SCRATCHPAD memory because I never have a SCRATCHPAD miss. It's always there. The disadvantage is, well, I have to manage the SCRATCHPAD memory in software. So it's more work for the programmer. So they're both trying to solve the same problem, to make loads happen fast by having the data close to the processor. And the differences are whether you do this entirely in hardware or entirely in software. So let's look at the GPU problem. When I have a GPU accelerated system, I've got a CPU connected to a GPU. The CPU's got a large system memory. The GPU has a much smaller but much higher bandwidth device memory. And today, for the most part, the device memory acts like a SCRATCHPAD memory. It's managed like a SCRATCHPAD memory. The software is going to allocate data in the device memory. It's going to copy data from the system memory into the device memory. So it behaves more or less exactly like a SCRATCHPAD memory. Now you may well ask, why don't I just connect them both to the same memory? Why do I need separate memories? It's a very good question. Well, it's economics. The cost per bit of my system memory is really low. The cost per bit of a high bandwidth memory is relatively high. Why do I want a high bandwidth memory? This is a highly parallel device. Highly parallel device does a lot of compute. It puts a lot of demand on the memory interface. There are two options for solving the memory interface demand. One is huge caches, and the other is higher bandwidth interconnect. Huge caches have a cost in that they chew up your real estate on your GPU chip. So now you're doing less compute, just storing data. That's a problem, that's a solution that's often used in CPUs because they're not quite so highly parallel. Here, I want to do more things in parallel. It's optimized for parallel execution, not for single-threaded execution. So if you're not going to have large caches, you need high bandwidth. High bandwidth, well, now you're into the high cost. High cost, you can't afford a lot of it, so you optimize to move the data in that you need and swap it out when you're done with it. So can we make the device memory act more like a cache? What would it take to do that? NVIDIA Volta GPUs, which not only can take page faults, but can be coherent with the system memory. And in fact, operating system modifications that will allow the GPU to take a page fault and to swap data from the CPU any memory in system memory. Unlike today with CUDA managed memory, it will be able to do this for any memory, whether or not it's been allocated with CUDA managed memory, dynamic memory, static memory, global memory, memory on the stack, any data at all can be paged over to the device when it's necessary and paged back. So what does this mean for the OpenACC programmer? Well, it means essentially the data directives become entirely optional. Just like when I'm programming for a multi-core CPU with the TA equals multi-core option, the data directives are more or less optional because the CPU knows that the data is all local anyway. I'm never going to make a copy of the data. I'm never going to move the data. When I have truly unified memory, then even on a device, I'll be able to access any data directly from the device, and the data will get paged over when necessary. So the data directives become essentially optional. Do they entirely go away? Not quite. Here we have demand paging. Demand paging is always just too late. What we want is to prefetch the data. Demand paging doesn't let me do that. So we'll repurpose those data directives so that when the OpenACC program sees a data directive saying, I'm going to be using data on the GPU, we'll either tell the operating system, this data, we prefer it goes over to the device as a block and stays there, or in fact start a prefetch over to the device. Because block transfers are always more efficient than page-at-a-time transfers, and prefetching means the data will be there before it's needed, and by the time it is needed, it'll be done. That's how we expect the unified memory feature to behave when we have the GPUs available, the Volta GPUs, and the operating system features implemented in the Linux operating system. And it's going to make everybody's life easier. It'll make programming these devices easier. Hope you found it interesting. Thanks for watching.